This lesson deals with supplemental problem 12.2. You can find this problem in the ECE202 ebook in the Chapter 12 Supplemental Problem starting on page 4. Given this series circuit with two resistors and a capacitor, can you solve for V out of S over V in of S, sketch the Bode plots of that, and then verify it with PSpice, and then draw your results from part B on top of the output plots. To save some space, I put the Spice file here at the beginning, and then we'll take a look at the results and compare it to our hand calculations. So I've got a title, I've got a dot end, got a voltage source between 1 and 0. It's a phasor with a magnitude of 1, so all my node voltages will be transfer functions. Resistor between nodes 1 and 2 with a value of 4.7K. Capacitor between 2 and 3 with a value of 470 picofarads. And then a resistor between 3 and 0 of 6.8K. The Bode plots will be mostly between 1 kilohertz and 1 megahertz. So I want to plot 3 decades, divide that by 200, and you get about 66 points per decade. V out is just a voltage divider with R2. And the impedance is R1 and 1 over SC1. That's the expression right here. Let's multiply numerator and denominator by SC1. So I get SC1 R2 divided by R1 plus R2 times SC1, and then just 1. Let's divide numerator and denominator by C1 times the quantity R1 plus R2. On the numerator, the C1s will cancel. I get R2 over R1 plus R2, and then I'll have the reciprocal of this in this term. Now putting the value in for R1 of 4.7K, and R2 6.8K, and C1 470 picofarads, I get the following results. 0.591 times S divided by S plus 185K. To do the Bode plots, we need to replace S by j omega. So we have 0.591 j omega divided by j omega plus 185K. The j omega, that's one of our forms. We'll pull out the constant 0.591, and from the denominator, let's pull out the 185K. We're left with 1, and then j omega divided by 185K. This ratio turns out to be 3.19 times 10 to the minus 6th. We are form 1. The j omega is a form 2. And then this reciprocal of real plus an imaginary term is our form 5. The 20 log of 3.19 times 10 to the 6th turns out to be a minus 110 dB. So here's a dashed line for the form 1. Form 2 passes through 1 radian per second with a slope of 20 dB per decade. So 1 decade changing of 20 dB. And lastly, the form 5 is 185 kiloradians per second. So we're going to then go to that frequency and then drop at 20 dB per decade. Now I'm going to add up the curves. Here's a region where all the slopes are constant. In region 1, I have a slope of 20 dB per decade, 0 dB per decade, and 0 dB per decade. So the sum is going to have a net slope of 20 dB per decade. Let's pick an easy point to add them up. I've got 0 for this curve, 0 for this curve, and I've got a minus 110 for this one. So this is my start point. And I drew a slope of 20 dB per decade up to 185 kiloradians per second. Then above that, I still have 20 dB per decade, minus 20 dB per decade, and 0 dB per decade. So we just level out at that point. I want to figure out what is the value here. I could try to measure it, but let's use our slopes to calculate it. So here's my unknown value of x. I know this is a minus 110 dB, so the difference of those two, first term minus the second term, then divided by the log of the ratio of their frequencies, which is 185K divided by 1. And that would be a slope of a plus 20 dB per decade. Cross multiplying by the log base 10 of 185K times the 20 dB per decade, I get a value, and then I'm going to bring this on the other side of the equation as a minus 110, and I wound up getting a net result of a minus 4.656 dB. The frequency of 185 kiloradians per second is 29.4 kilohertz if you pull out the 2 pi. Now let's take a look at the phase angle. Our constant was a positive, so the phase angle is 0. And then we had a j omega, which is a phase angle of 90 degrees. On the form 5, we have an omega c of 185K, so we're going to drop 45 degrees at that frequency. If you go back a decade, it's 0. If you go forward a decade to 1.85 meg, you'd be down to minus 90 degrees. What we're doing is adding a constant to this graph. It's going to lift it up to 90 degrees. Start out at 90, and then we eventually get back to 0 degrees. Let's take a look at what the SPICE results look like. My output node was node 3. My input was node 1, but my input is equal to 1 volt, so node voltage 3 is the transfer function. I'll do this in dB. And here's the actual curve. And then with the cursor, I measured the value. It was a minus 4.568 dB, so very close to what we hand calculated. The corner frequency was at 29.4 kilohertz, and so I found where that was between 10K and 100K using my ruler, the techniques described in Chapter 12. Then I drew my asymptotes from that point. Below that, a slope of 20 dB per decade, and above it 0 dB per decade. And right at this frequency, we're roughly down 3 dB. The phase angle of my voltage gain is the phase angle of the numerator, which is node voltage 3, minus the phase angle of the denominator, which is node voltage 1. Node voltage 1 is at an angle of 0. So here's my actual curve, going from roughly plus 90 degrees to 0. Found the frequency 29.4 kilohertz, That's where we would be at our 45-degree point. Go back a decade, go forward a decade, and we'll change a total of 90 degrees. I drew my asymptotes in. And so our hand calculation is very close to the actual simulation. And this is supplemental problem 12.2.